तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last two classes we were discussing about anaerobic process. We have seen what is the fundamentals of anaerobic process and what are the parameters or what are the environmental conditions required for the proper functioning of anaerobic process and why the anaerobic process was not becoming popular in the recent past. And we have seen in detail about the high rate anaerobic processes or anaerobic reactors which is commonly used nowadays, which can retain large quantities of biomass inside the system. And we were discussing about UASB reactor, the upflow anaerobic sludge blanket reactor, which is the one most commonly used for the domestic wastewater treatment, especially in tropical countries. So we have seen how to design the reactor, how to design the settling zone, how to design the gas, liquid, solid separation systems, etc. in detail. And now we will discuss about the design of inlet as well as the outlet arrangements in a UASB reactor, and further we will discuss about how the sludge, whatever is coming from the biological treatment systems as well as chemical treatment systems, can be handled. So this is a picture or figure we were discussing in detail last class. So this is a schematic of an upflow anaerobic sludge blanket reactor, and we have seen how it is functioning. The wastewater is coming like this and the influent is getting equally distributed in the bottom of the reactor, and the biological sludge, which is flocculent in nature, it will be in the bottom of the reactor. As the wastewater passes through that one, it will pass through this sludge, which is nothing but active biomass. So the biomass will be in contact with the organic matter present in the wastewater, so it will be undergoing degradation. As a result, new biomass will be generated and the liquid will be coming up, the biomass will be coming up, as well as the biogas, whatever is generated as the byproduct of microbial degradation, also will be coming up. But if the solids escape along with the liquid, then the efficiency of the system will be coming down. So we are providing a specific system here, including this deflector beam and this cone arrangement. This is known as gas liquid solid separator, and we have seen in detail how to design this one, and the basic objective of this GLSS is to separate solid phase, liquid phase and gas phase, so that all the biomass will be retained in this digester zone and the biogas will be collected here and we can use it for other purposes, and we get completely treated clear effluent here which can be discharged without any problem. This will be meeting the effluent standards. So we have discussed in detail about the digestion zone design, settling zone design and GLSS design. Now we will see how to design the influent distribution device. It is very important, the distribution of wastewater in the reactor, because if uniform distribution is not there, then the contact of organic matter and the microorganism will not be proper. So the efficiency of the system can come down, because if the distribution is not uniform, short circuiting can take place in the system. So only a very little amount of organic matter will be coming in contact with the active biomass. So naturally the treatment efficiency will be coming down. So for the proper functioning of an anaerobic reactor or a UASB reactor, the uniform distribution is essential. This is done using flow splitting devices. The recommended value is at least one inlet should be there for every 1 to 2 meters squared of the reactor area. And why this uniform distribution is essential, or how can we guarantee the uniform distribution? So we have to verify these points, or we have to take care of following things. So one should verify the flow at each inlet point. Though we provide a proper distribution system, if choking takes place in certain points, then what will happen? The distribution of the wastewater in the reactor zone will not be proper. So definitely there will be short circuiting and some zones will not be getting any organic matter. So that will be adversely affecting the reactor performance. So verification of flow at each inlet point is very essential, and obstruction of inlet point should be detectable, and if obstruction is found, it should be removed. So these are the important points to be taken care to get a uniform distribution in the reactor. So this shows a distribution system. So you have, this is the where the water is coming here, and this is the distribution well. It is going to different points. You can see this one. From here it is coming to each inlet point, and the main influent is coming like this, and this is the weir, and from here it is getting distributed to various inlet points, and it will be going down. And this inlet, either it can be from the bottom of the reactor and using a nozzle, and the nozzle opening will be in the bottom of the pipe. The reason is, if the nozzle is facing to the sludge, what will happen? The sludge will be entering in the nozzle opening and the nozzle will be getting clogged. So usually what will happen, a ball type or bell type arrangement will be there in the inlet of the inlet tube. So what will happen, that will be covering, or that will be preventing the tube getting clogged because of the sludge, and the wastewater will be entering from both sides and it will be going up. So it will provide a proper distribution of the wastewater. In some other cases, what is usually done is, the inlet will be coming from the top of the reactor straight to the bottom. So what will happen, because of the hydraulic pressure, it will be getting distributed, so the choking can be avoided in that case. So this is the arrangement usually used in circular devices, and this is a rectangular inlet device. And the effluent collection devices are also very important. The effluent collection devices usually employed in UASB reactor are very similar to the ones which we use in sedimentation tanks. We have gutters with V notches to collect the effluent at the top of the UASB reactors. See, here we can see the gutters with V notches, so it will be getting collected here, and the effluent is coming from here, and it will be going for either further treatment or to disposal. So this is the alternate design for effluent collection systems. So whatever we have designed or we have discussed in detail for sedimentation tank, so same type of, because we know that in the UASB reactor the top portion will be acting as a sedimentation tank. So same type of an effluent collection device we can use for the UASB reactors. Now whatever we were discussing till now about the anaerobic treatment systems, but these anaerobic treatment systems in most of the cases cannot be used as a single treatment process for meeting the effluent discharge standards. The reason is, anaerobic process will not be able to take care of the pathogens whatever is present in the wastewater, or the microbial concentration whatever is present in the wastewater. It will be getting reduced only 1 log order or 2 log order. So we have to have a proper post treatment unit to take care of these things. And moreover, in UASB reactor, because we know that the substrate is not getting oxidized or anything, and the biomass synthesis is very less. We have seen that the anabolism, the organic matter whatever is entering in the system, only 8% is going for anabolism, or the sludge generated in anaerobic process is very less compared to the aerobic process. And we know that for the microbial cell synthesis, the nutrients are essential. So if more cells are synthesized, then definitely more nutrients present in the wastewater is used for that purpose. But in anaerobic system, since the microbial concentration is so less, the nutrients used for cell synthesis is very negligible. So as a whole treatment unit, if you take the anaerobic process, what will happen, there will not be any nutrient removal like nitrate or ammonia whatever present, that will be remaining as such. The one which is escaped through the gas phase will be getting removed from the system, otherwise everything will be getting accumulated in the wastewater treatment or in the anaerobic treatment system itself. Similarly, phosphorus also, it will be getting accumulated or it will not be getting removed from the system. So if you want to use it as a treatment unit, and if you want to meet the effluent discharge standards, whenever we go for an anaerobic treatment system, we should have post treatment. So that is what I have given here. No nutrient removal is taking place in an anaerobic system. So and very little pathogens removal is taking place. So usually after the anaerobic treatment process, we give post treatment, and most of the time the post treatment is either an activated sludge unit or an oxidation pond or a maturation pond or an extended aeration system, because we know that all the minerals or all the inorganic substance whatever is present in the wastewater, it will be in the reduced condition when it comes out of the anaerobic reactor, because in anaerobic reactor complete anaerobic condition or an environment which is conducive for reduction is existing. So whatever is there, it will be coming out in the complete reduced form. So when we discharge it to the existing water bodies, what will happen? This reduced form of the minerals or the material will have a tendency to get oxidized. So definitely there will be an oxidation or oxygen demand in the system. So if you directly discharge the anaerobic effluent to a water body, there will be some BOD exerted by the treated effluent. So it is always advisable to go for a post treatment, and which can take care of the oxygen demand as well as the nutrient removal along with the pathogen removal. Okay. Till now we were discussing about how to remove the organic matter from the wastewater. We have seen in detail aerobic process, anaerobic process, both attached systems and suspended systems. And when we were talking about aerobic systems, we have seen that in activated sludge process itself, there are various process modifications, and depending upon the process we are selecting, the sludge generated will be varying. For example, in a conventional activated sludge process, whatever organic matter we are giving, say if we are giving 1 kilogram of organic matter, around 400 to 500 milligrams will be coming as sludge or active biomass, and we will be removing it in the secondary sedimentation tank, and it will be coming out as a sludge. But if you go for extended aeration system, what is happening? Most of the biomass whatever is generated in the system, it will be getting auto oxidized, and we will be getting only very little amount of sludge. Similarly, in anaerobic process also we will be getting a certain amount of sludge, whether it is microorganism or the inorganic material whatever is present in the wastewater. So there is a need for the proper handling of this sludge, or sludge treatment is very essential, not only in biological systems but also in physicochemical processes. We have seen that whenever we go for coagulation flocculation, what will happen to the sludge whatever is collected in the coagulation flocculation or sedimentation tank after the coagulation flocculation, that sludge also we have to take care. So now we will discuss about the sludge treatment. What are the different ways we can handle the sludge, or what are the precautions we have to take while handling the sludge. Okay. So we will talk about the sludge treatment. So nowadays the sludge treatment, okay, it is known as biosolids treatment. Okay, sludge means something not useful or something not desirable, that is the meaning of sludge. But biosolids, once we call it as biosolids, that means if we can give some treatment and we can get something which is having a certain beneficial value, then definitely we can call it as biosolids. So in the new or recent edition books, they talk about biosolids treatment. So what treatment we can give so that the end product whatever we are getting, it is having some beneficial use. And before going for the sludge treatment, we have to see what are the different sources of this sludge and what is the characteristics of the sludge coming from different treatment units, and what is the amount of the sludge which is coming. Then only we can go for or the selection of the process which is most economical or most viable for that particular system. So if you talk about a water treatment plant or a wastewater treatment plant, sludge can be generated from various sources. So these are the solid sources. First one is screening. In screening we will be getting coarse solids, because we know what is the purpose of a screen. And in grit chamber we will be getting grit and scum, and in pre-aeration unit we get grit and scum again, and in primary sedimentation unit we get primary solids and scum. Primary solids means it will be basically organic matter, and in biological treatment systems either it is an activated sludge process or a trickling filter or an anaerobic process, we will be getting suspended solids as the sludge, and in secondary treatment secondary biosolids and scum will be coming, and in solid processing facilities we will be getting solids, compost and ashes. So these are the different sources of sludge or the biosolids whatever is coming in a wastewater treatment unit. And now we will see what is the characteristics of this sludge or the solids whatever we are getting from different treatment units. The characteristics will be entirely different because each unit is having its own purpose, because screen, we know what is the purpose of a screen. It will be removing all floating and large size particles, and if you come to a grid chamber we know that its main purpose is to remove grit or inorganic material which is having high settling velocity, and we know that the purpose of a primary sedimentation tank is to remove the suspended organic matter. And when we come to a biological treatment unit, the sludge will be completely active microorganism, and when we talk about the chemical treatment units, the sludge will be of a mixture of the pollutant as well as chemical. So it is essential to know the characteristics of the sludge before going for a particular treatment. So we will see the characteristics of the sludge from each unit. So the screenings, whatever the solids whatever is collected in the screen, it will be having all types of organic and inorganic materials, and they will be large in size and composition varies depending on the system. So this is the characteristics of the screenings or the solids collected in a screen. And now coming to grid chamber, the material collected we call it as grid. It is heavier inorganic solids that settle with high velocity, because the basic design itself is meant for removing heavy inorganic materials from the wastewater, because if it goes to the further treatment or secondary treatment units, what will happen, it will be adversely affecting the pumping system and all, because it will create lot of wear and tear, and unnecessarily we will be getting the sludge which is not active. So to prevent that one, we provide the grid chamber. So this is the basic character of a grid, and sometimes it contains organic matter, for example fat and grease, because if the settling time whatever we are providing is very high, then definitely along with the inorganic material, the organic material also will be settling down. So the grid may contain some portion of organic matter like fat and grease, and this grease can get attached to the inorganic material and it will be settling or floating along with that one. Now coming to scum and grease, so we know that we certain cases we put the scum remover or grease remover. So definitely the solids whatever is coming from there, it is floatable in nature, and it consists of grease, vegetable and mineral oil, animal fat, waxes, soaps, food waste, vegetable and fruit skims, and its specific gravity varies from 0.95 to 1. So that is the characteristics of this scum or grease. And now we will see what is the characteristics of primary sludge, whatever we are collecting in the primary sedimentation tank. Mostly it will be organic in nature, and it is easily digestible matter because it is not undergoing any biodegradation there, and we know that lot of suspended solids will be present in the wastewater. So in the primary sedimentation tank, around 50 to 60% of the suspended solids in the wastewater will be getting removed, and we have seen that the screens and grid chamber will be removing almost all the inorganic material which is heavier and having high settling velocity. So definitely this primary sludge will be organic in nature and easily digestible. Now we will see what is the characteristics of the sludge from a chemical precipitation unit. Usually the sludge will be dark in color and degradable at low rate. The reason is organic matter will be there and some inorganic matter will be there. To remove that one, we are adding certain chemicals to change the property of the material or the solids present there. So because of that chemical addition, what will happen? we will be getting a mixture of organic as well as inorganic sludge. Definitely because of the presence of this inorganic material or the chemical, the degradability of the sludge, whatever we are getting from a chemical precipitation or chemical treatment plant will be less compared to the primary sludge, whatever we are getting from a primary sedimentation tank. Now coming to the sludge, whatever we are getting from a activated sludge process. Usually the color of the sludge will be brown and it is flocculent in nature, and if the sludge becomes septic, then it will become dark, and if the sludge is in good condition, it does not have any smell or it is inoffensive and it will be having an earthy odor, but if it is dark and septic, it will be generating offensive odors. So this is the nature of activated sludge, and mostly it is organic matter. And now coming to the trickling filter, we know that whatever the biomass present in the trickling filter, once it slaps from the material or the support media, what will happen? It will be coming along with the liquid, whatever is trickling through the biofilter, and in the sedimentation tank, the biomass will be settling down. So that is the sludge whatever we get from a trickling filter. The sludge from a trickling filter is usually brownish in color and they are flocculent in nature. Compared to this activated sludge, the trickling filter sludge digests slowly, and sometimes this sludge contains many worms. The reason is it is getting exposed to these flies and all, so that flies lay eggs on the trickling filter. So definitely many worms and larvae will be present in this sludge. And if you want to find out the characteristics of aerobically digested biosolids, because whatever the sludge we are getting from all these process, either from primary sedimentation tank, activated sludge process or trickling filter, we can take care of or we can treat the sludge or reduce the volume of the sludge by further aerobic digestion. So if you go for this aerobic digestion and if you want to find out what is the characteristics of the sludge, whatever is left over after the digestion, they will be either dark brown in color, and of course they are also flocculent in nature and there is no offensive odor, and well digested sludge dewaters easily on digestion beds. Okay, that is one advantage. If aerobically, if you take the sludge from activated sludge and trickling filter and if you try to dewater it, it is very difficult. But once we digest the sludge, then if you want to dewater it, it will be much easier to dewater compared to the undigested sludge. Now we will see what is the characteristics of anaerobically digested biosolids. Most of the time these biosolids are completely stabilized and it is black in color, contains large quantities of gas, and tried sludge, if you want to find out the property of tried sludge, it is having well cracked surfaces resembling that of garden loam. So this sludge, anaerobically digested biosolids or the sludge, we can directly dispose of in drying beds because that does not have any malodors or anything. And now coming to compost, because compost is a method to treat the biosolids. So after composting also we will be getting some solids left over. So the solids whatever we are getting from composting is dark brown to black in color and they are well digested sludge and inoffensive, and we can use it as manure or soil conditioners. So this table gives us the basic properties of the sludge whatever we are getting from various treatment processes. Okay, if you take the primary sedimentation tank, the specific gravity of the solids is in the range of 1.4, but if you want to find out the specific gravity of the sludge, it is only 1.02, because though the solids are having high specific gravity, okay, we know that the sludge will be containing lot of water, around 95 to 96% of water, and the solids is only 2 to 4%. So the net specific gravity of the sludge will be very less, almost equal to the water, 1.02. And activated sludge, whatever is coming from the secondary sedimentation tank waste, the specific gravity of the solids is around 1.25 and specific gravity of the sludge is only 1.005. And trickling filter, it is having a better specific gravity of 1.45, but the sludge specific gravity is only 1.025, and extended aeration it is 1.3 and it is 1.015, because extended aeration sludge will be mostly inorganic in nature, because whatever the organic matter or the biomass present in the system will be getting auto oxidized during the aeration process. And in aerated lagoon, the specific gravity of the sludge is 1.3 and specific gravity of the sludge is 1.01. This is the solid specific gravity. And filtration, it is 1.2 and 1.005. And if you want to remove the algae from the oxidation pond, the specific gravity of the solid is 1.2 and specific gravity of the sludge is 1.005. These values are very important, because it decides what is the volume of the sludge we have to handle, because the volume is very important when we design the treatment systems. Okay. Similarly, I have put the specific gravity of the solids and sludge for chemical treatment. If you go for lime treatment, the specific gravity will be 1.9 and 1.04. If high lime process, 2.22, 2.2 is the specific gravity of the solids and specific gravity of the sludge is 1.05, and denitrification 1.22, 1.005, and roughening filters it is 1.28 and 1.02. And if you want to find out what is the solids concentration coming out, because we have the sludge and we know what is the volume of sludge coming, and if you want to get an idea what is the amount of solids present, so this table gives this idea. Primary sludge from a primary settling tank, the percentage solids varies from 5 to 9 and typical value is 6. Similarly, I have given primary sludge with low lime addition for phosphorus remover. The solid concentration varies from 2 to 8, and iron salt addition for phosphorus remover, the solid concentration is 0.5 to 3. So we know that what is the treatment unit, and we can get corresponding solid concentration here. So we will be knowing what is the amount of, or what is the mass of solids we have to destruct, and what is the volume of sludge. Similarly, this gives the secondary treatment. Okay, waste activated sludge with primary settling, the solid concentration of the sludge varies from 0.5 to 1.5. That means around 98.5 is water, because we will be having such a huge volume and the sludge is only very little. And waste activated sludge without primary settling, it will be little more, because the solids whatever is not removed in this one, some inorganic solids also will be there. So definitely the solid concentration in the secondary sedimentation tank will be increasing. And if you see what is the sludge concentration or solid concentration in RBC, it is varying from 1 to 3. Similarly, trickling filter also the range is 1 to 3, and typical design value we take it as 1.5. And here I have again given gravity thickener and flotation thickener and centrifuge thickener. The solid concentration varies from 5 to 10 and 4 to 8. So we can see that in any case we take, the solid concentration is most of the time less than 5%, and the remaining 95% is water. And this is anaerobic digester. The primary sludge, if you want to go for the solid concentration, we are taking as 2 to 5, from waste activated sludge 1.5 to 4, because this solid concentration is essential, especially when we go for the stabilization unit design. So, and these tables are available in design manuals and all those things. So we can get a rough idea about what is the solid concentration usually present in the sludge whatever we are getting from different treatment units. So, and I have already told this is essential when we go for the design. Now we will see, okay, we have seen that there will be lot of water present in that one, and there will be different types of solids present in the sludge whatever is coming from various treatment units. For example, if you take the sludge from a activated sludge process, it will be having both aerobic, both volatile organic matter as well as fixed suspended solids or fixed matter, that means organic and inorganic. So when we design a stabilization system or a biosolids treatment system, the inorganic solids we are not going to do anything, because we cannot remove that one from the system, that volume will be remaining as such. But the volatile solids or the organic solids, that we can remove by biological treatment systems or by chemical treatment systems. So it is essential to find out what is the volume of the sludge and what is the mass of the sludge and what is the mass contributed by the fixed solids and what is the mass contributed by the volatile solids and vice versa. So we can use this formula if you want to find out what is the volume of the sludge or what is the relationship between volume and mass of a sludge. So this formula is nothing but Ws by Ss by rho W is equal to Wf divided by Sf into rho W plus Wv by Sv into rho W. Here Ws is the weight of solids, total solids, and Ss is the specific gravity of total solids. That means it includes both volatile as well as fixed solids. And rho W, as all of us know, it is nothing but the density of water. And Wf is the weight of fixed solids and Sf is the specific gravity of fixed solids and Wv is the weight of volatile solids and Sv is the specific gravity of volatile solids. So if you know what is the weight of fixed solids and volatile solids and what is the specific gravity of fixed solids and specific gravity of volatile solids, we can find out what is the volume of total sludge or what is the weight of total sludge, etc. Now we will see a problem how to find out the specific gravity of solids as well as sludge. Okay, this is the problem. 1/3 of the solid matter in a sludge containing 92% water is composed of fixed mineral solids of specific gravity 2.6 and 2/3 is composed of volatile solids. The specific gravity of solids can be calculated as given below. Okay. So before that, once again we will read the problem. The sludge containing around 92% of water and only 8% of solids, and in the solids only 1/3 is composed of fixed mineral solids and 2/3 is volatile solids, and fixed mineral solids specific gravity is 2.6. Okay. So these are the informations we have. So first what we have to do, we have to find out what is the specific gravity of the solids alone. Okay, we are not considering the water initially, we are finding out the specific gravity of the solids alone. So we can use this formula 1 by Ss is equal to, so what is the fraction of fixed mineral solids divided by its specific gravity plus what is the fraction of volatile solids by its specific gravity. So this is, okay, we know that only 1/3 is fixed mineral solids, so this will come as 0.33 divided by 2.6, okay, plus 0.67 by 1. We are assuming the specific gravity of volatile solids is almost same as that of water. So we will be getting 1 by Ss or 1 by specific gravity of the solid as 0.80 or specific gravity of the solids as such is 1 by 0.80, that is equal to 1.25. So this is the specific gravity of solids alone, but we know that in the total sludge around 92% is water and only 8% is solids. So now the next step is, okay, we have to find out what is the specific gravity of the sludge as such. So if the specific gravity of water is taken as 1, then the specific gravity of sludge SSL, okay, this is the solids along with the liquid or the sludge, that we can calculate as follows: 1 by SSL is equal to fraction of solids by its specific gravity plus fraction of water by its specific gravity. So we know that only 8% is solids, so 0.08 by 1.25 plus 0.92 by 1, which is equal to 0.984. Okay, this is the 1 by SSL or 1 by specific gravity of the sludge as such, or the specific gravity of the sludge SSL is equal to 1 by 0.984, which is equal to 1.02. We can see that the specific gravity of the sludge is almost same as that of water, only slight difference is there. And if you want to find out the volume of the sludge, we can use this one. We know what is the total mass or weight of the sludge divided by rho W into SSL into PS, where volume, V is the volume of the sludge in meter cube, MS is the mass of dry solids in kilogram, Rho W is the specific gravity of water, and SSL is the specific gravity of sludge, and PS is the percent solid expressed as decimal. So, if you know the percentage solid percent as a fraction and mass dry weight, then we can find out what will be the volume of the sludge. Now, okay, we have seen how to calculate the specific gravity of the solids as well as the specific gravity of the sludge, and if you know the solid concentration as weight, then we know how to calculate the volume of the sludge. So, all these informations are available, and we know that from each unit, okay, what is the nature of the sludge coming, and what is the amount of the sludge coming, and what is the solid concentration that is coming out. Okay, we have seen all those in detail. Now, we will see what is the process we have to use for the solids handling. So, this is the solid processing flow diagram, because it involves lot of processes. So, I try to put everything in this single block diagram. So, the solid flow is coming like this, and initially it is going for the preliminary operations. The preliminary operations consists of grinding, degridding, blending and storage, because we know that the solids whatever is coming from different units, screens, grids, etc., it will be having very high sizes. So, we have to go for all these preliminary operations to make or to get a uniform characteristics solids. Once the solids are there, and we know that the water content in these solids will be very high, or the sludge solid content will be very less. So, if you send the sludge like that to the treatment unit, definitely the treatment unit volume will be very high, and the chemical requirement will be very high. So, it is always advisable to dewater the sludge as much as possible before sending it to stabilization. So, the second operations in a solid processing flow diagram is thickening. Thickening is nothing but remove as much as water as possible. So, this can be achieved either by co-settling or gravity settling, or by flotation, or by centrifuging, or gravity belt process, or rotary drum. So, these all are the thickening process. Anyway, we will see each process in detail afterwards. So, here I am trying to give a basic flow diagram how we can manage the solids. Once the thickening is over, then we have to go for the stabilization. Stabilization is the process by which we stabilize the sludge. That means we remove the pathogens present in the sludge, make the sludge in such a way that further purification is not possible. So, this stabilization can be achieved either by chemical process, that means most of the time we go for lime stabilization, then we can use aerobic processes and anaerobic digestion. So, these are the most commonly used stabilization process. Once the stabilization is over, again the sludge will be containing lot of water. So, it will be very difficult to send it to sludge drying bed or another land applications. So, the next one is conditioning. Conditioning improve the quality of the sludge, or it will be improving the dewatering property of the sludge. That is the purpose of this conditioning. The conditioning can be done either by chemical means or other means. Other means either thermal or other processes. Once the conditioning is over, then we go for dewatering. Dewatering, as we have discussed here in the thickening, same process can be used here, either centrifuging, belt filter press or filter press, or even we can go for sludge drying beds or reed bed. Even lagoons can be used for this dewatering purpose. Only thing, we have to allow the sludge to stay there for long time. With respect to time, the water, whatever is present in the sludge will be getting out of it, and we will be getting relatively dewatered sludge. Once the dewatering is over, next step is drying the sludge. Okay, the drying can be done either by direct layer or in sludge drying beds, or indirect layer method, or composting, alkaline stabilization and pasteurization, long term storage. All this process can be adopted for the heat drying process. After that one, okay, if you want to further reduce the sludge volume, we can go for thermal reduction. That means we can go for different types of incineration process, because we have got the sludge already thickened and dewatered and tried one, and either we can apply to the land, and if you don't want to use that process, and if you want to further reduce the volume, we have to go for thermal treatment or incineration, and the various types of incinerators can be used for this purpose. Okay, now we will see what are the processes we usually use in wastewater treatment plants. So, if the waste activated sludge is coming from an activated sludge process, first we go for a thickener. Okay, thickener we have seen in detail how to design a thickener. The secondary sedimentation tank itself will be acting as a thickener. So, here the sludge from the activated sludge process as well as the sludge from the primary sedimentation tank can come and the thickening can take place. Then it will be going to anaerobic sludge digester, and whatever the supernatant is coming, it will be separated and sent for further treatment, and whatever is the sludge coming from the anaerobic treatment system or the anaerobic digester, usually it undergoes chemical conditioning. If we are going for belt filter press for the dewatering, because chemical conditioning is required, because in this belt filter, when we discuss in detail, we will be knowing why this chemical conditioning is required. Once the dewatering is completed, okay, it can go for disposal or for further processing or land application. So, this is one of the methods we can adopt for handling the sludge from a waste activated or the sludge from an activated sludge process. And this is another system. This is a combined thickened waste activated and primary sludge. So, it is going for anaerobic sludge digestion, then chemical conditioning. Here the only difference is, instead of going for a belt filter press, we can go for a centrifuge. So, definitely the centrifuge also will be dewatering the sludge and we will be getting tried sludge, and the tried sludge we can send it for disposal or for further processing or for land application. And this is the third alternative, the combined waste from the activated and primary sedimentation tank is coming, and again we are going for anaerobic digestion, and the plant effluent whatever is coming, it is going for further treatment. And here we are not going for any chemical conditioning or anything, because the trying step is not either centrifuging or belt filter press, we are using only trying beds. So, this trying beds, we are allowing the sludge to retain or stay there for a long time. So, within that time, whatever is the water present in the sludge, it will be drying out, and because of the solar radiation or the temperature coming from the solar radiation, the remaining water will be getting evaporated and we will be getting a dried sludge which can be disposed of, or it can be processed further, or we can use it for land filling. Now, we will see what the flow chart we have seen, what are the steps involved, we have seen in detail. We have seen what are the process that is required for the complete handling or complete treatment of this biosolids or the sludge generated from the various treatment operations and process of wastewater. Now, we will see each process in detail. First, we will talk about the preliminary operations. As we have discussed earlier, the preliminary operations consist of grinding, degridding, etc. What is the grinding, degridding, blending and storage of solids? Okay, these are the preliminary treatments. The purpose of this preliminary treatment, as we have already discussed, is to get a relatively homogeneous feed to the subsequent facilities. This is the major objective of this preliminary operations. So, what we are doing in a grinding, or why grinding is essential? Because we know that the solids whatever is collected in the screens, they will be large in size. So, grinding is essential for large and stringy materials are cut or shredded into small particles to prevent clogging or wrapping around rotating equipment. Because if we won't do this one, what will happen? The large particles will be going to the next or the other treatment units. So, it will be clogging the pumps and other operating systems which is having moving parts. So, it is essential to cut them or shred them into smaller pieces. So this grinding is essential for the screenings, because the screening is meant for, okay, this grinding will be doing that one, and the screening will be removing the nuisance material whatever is coming from the after grinding, also some floating material which is larger in size, which is not grinded properly, okay, that will be getting removed in the screens. And in degritting, what we are doing is, if you do not have a grit chamber, or if the grit chamber is not functioning properly, then definitely this inorganic material will be coming along with the biosolids. So the sludge will be containing both organic and inorganic solids. So if the grit or the inorganic solids are present along with the sludge, what will happen? The pumps whatever we are using for the sludge pumping and all will be getting affected by this grit. So it is very essential to remove the grit or the heavy inorganic material whatever is present in the biosolids. So it is necessary when no grit chambers are provided before the primary settling. The purpose is to remove the grit whatever is present in the biosolids, and blending is the process in which the mixing takes place so that finally we get a uniform characteristic sludge. So we are grinding it, then we are screening to remove the nuisance material, then we are going for degritting. Degritting will be removing all the grit material. Once these three operations are done, then what we do, we will be blending the sludge, because we have seen that the characteristics of the sludge whatever is coming from different operations are entirely different. So if you send one by one to the treatment system, the treatment system will be getting the feed of so much varying characteristics. So it will be affecting the efficiency of the treatment system further whatever we are going to adopt for stabilization and other processes. So it is essential to send somewhat homogeneous sludge to the further treatment units. So that is the purpose of this blending. Then now coming to the storage, to smooth out fluctuations in the rate of solids production, because we know that the solids whatever is coming from the different treatment units, it will not be continuous in nature, because the screens or the screenings whatever we are getting, whenever the screen gets clogged and when the pressure drop is more than the permissible limit, then only we go for the cleaning of the screen. Once the screen is cleaned, we are getting the solids from the screen. So definitely it is not a continuous one. And similarly, in the activated sludge process also, in most of the cases, the sludge wastage is not on continuous basis. Daily 1 or 2 times or 3 or 4 times we will be wasting the sludge. Similarly, in other biological process and chemical process, the sludge wastage will not be a continuous one. So in such cases, if we allow the sludge whatever is coming from the treatment units as such to the biosolids handling units, then the efficiency of the system will not be proper. So in such cases what we have to do, we have to blend the sludge and store it in a storage tank which will be equalizing the flow of the sludge, and from the storage tank we can supply a specified quantity or a uniform quantity to the further treatment units. So the sludge storage tank will be functioning exactly the same way as that of a equalization tank in a wastewater treatment system. So this storage is also very essential, which smooth the fluctuations in the rate of solids production. Okay. Now we will talk about the thickening. The preliminary process is over, and we know that the solids whatever is coming, okay, it will be having less than 5% of solids. So if the solid concentration is less than 5%, we can imagine remaining 95% is water. So because of this water content, the treatment unit whatever we are going to provide, the volume will be increasing considerably. Definitely the treatment cost or the capital cost for the treatment unit will be increasing drastically. So if we can reduce the water content considerably, then definitely your further treatment units volume will be reducing significantly. So that is the very purpose of this thickening. Okay. The main function is volume reduction by sludge concentration, and the advantage of this thickening is the capacity of tanks and equipment required can be reduced, because we know that the solids is only less than 5%, remaining capacity is only to handle the water, whatever is present in the solids. So if we can remove that one, we are only interested in handling the solids. So the capacity of the tanks and the equipment required can be reduced considerably. Then definitely the quantity of chemicals required can be reduced. The reason is, if you go for chemical conditioning or chemical stabilization, if you want to add the chemicals, definitely we have to add the chemicals to take care of the water, whatever is present in the sludge, because if the water content is more, the chemical whatever we are adding, it will be getting diluted and the effect will be less. So we have to add more amount of chemical to take care of the dilution aspect. So if you can remove the water content from the sludge considerably, definitely the quantity of the chemical to be added can be reduced significantly. And if you talk about the heat treatment, the amount of heat required can be reduced, because if the moisture content or the water content is very high, definitely the heat required will be very high. So if you can remove that one, the energy involved or the heat what we have to supply to achieve the same degree of treatment can be reduced considerably. So what are the methods commonly used for thickening? So they are co-settling thickening, then gravity thickening, flotation thickening, centrifugal thickening, gravity belt thickening and rotary drum thickening. So these are the most commonly used methods for the thickening. So in co-settling, what is happening? We will be having various clarifiers, and the sludge from the clarifiers will be coming to the thickener. Similarly, the overflow from the clarifiers also will be coming to the thickener. So because of this one, a proper thickening will be taking place in the thickening tank, and it will be considerably reducing the sludge volume. And gravity thickening we have already discussed in detail when we were discussing about the secondary sedimentation tank design, because in actuated sludge process and all, whenever we design the secondary sedimentation tank, it has to satisfy two criteria. One is the clarification and another one is sludge thickening. So we have to find out the area of the secondary sedimentation tank based upon these two criteria, and we have to provide the area whichever is coming more, either the area corresponding to the clarification or the thickening. And the thickening area we can find out using the solid flux theory, and we have seen in detail how to find out the area and how to design a gravity thickening unit. So this shows the picture of a gravity settler. So it is nothing but a sedimentation tank. Only thing, when we design, the overflow rate, loading rate, etc. should be and cross-sectional area should be provided based upon the sludge thickening characteristics. So this is a circular type sedimentation tank. So this is the entrance of the sludge. It will be getting distributed like this. Okay, this is the pressurized wastewater entrance. It is coming here. It is getting distributed like this. Okay, and here it is getting settled, and clear liquid will be going out like this, and sludge can be collected through this one. Okay, this is the sludge collector, and here we have a retention baffle. This will help the solids to enter into the liquid. So what will happen? More and more clear liquid will be getting removed from the system. So definitely whatever the solids we are getting here, it will be having a high density compared to whatever we are supplying. So this is a thickener. Flotation unit, we all know, if the solids density is less, then instead of going for gravity settling or settling, we can concentrate it by flotation. So flotation also we have discussed in detail when we were discussing about the solid removal. And centrifugal thickening, here we use the centrifugal force for the thickening. And in gravity belt thickening, what is happening? The sludge will be placed on a belt and the belt will be moving, and with respect to time what will happen? Whatever is the water present in the sludge will be gradually oozing out, and we will be getting a relatively concentrated sludge towards the end of the belt thickener. And rotary drum thickening also, the drum will be rotating, and because of the rotation what will happen? the liquid will be getting removed from the sludge and we will be getting a concentrated sludge. And I will show few photographs of this centrifugal thickening, gravity belt and rotary drum thickening. So this is a centrifugal thickener. So here we can see that the free solids are entering here and it is getting out in the system here. It is coming through the central shaft and it is getting out here, and as we all know, okay, this is the gearbox and this gearbox will be rotating at a differential speed. So what will happen with respect to time? Okay, the solids will be getting pushed to the periphery of this drum, and this is the rotating drum, and we can see that this is having a tapering section. So as the solids move towards this side, more and more compression will be taking place and the water will be getting discharged from the sludge, and here we will be getting somewhat concentrated sludge, and this we can remove using this pot, okay, here and here. So the drum will be rotating and the feed is coming from the center, and because of this one it is getting thickened. So this is the centrifugal thickener and this is a belt thickener. Here we can see that the liquid sludge is coming, we are adding some polymers and that is coming here, it is moving through the belt, and because of this one gravity drainage is taking place. So water is getting removed, and this portion, this is meant for belt washing. So as it moves, the sludge will be getting dewatered and here we get more concentrated sludge. We have seen in detail what are the different process we have to adopt for the solid stabilization. We have seen the flow diagram. So preliminary treatment is required, then we have to go for dewatering. The reason is the water content in the sludge will be very high and solid concentration will be less. So definitely it will be increasing the volume of further treatment. So once the dewatering is done, then we can go for stabilization. The purpose of stabilization is to remove the pathogens and to destruct the organic matter so that there will not be any further putrefaction. And once the stabilization is over, we can go for conditioning and again dewatering, then drying, then disposal. But in usual wastewater treatment plants, especially when we go for the biological treatment systems, we have seen that either in the activated sludge or the sludge coming from trickling filter, usually we go for dewatering, then anaerobic digestion, then if you are going for belt thickener or centrifuge, we have to go for chemical conditioning. But if you are going for sludge drying beds, this conditioning is not required, because in the sludge drying bed itself we are giving lot of time for the water to get removed from the sludge so that we can get a dry sludge which possesses less volume, and this sludge whatever is coming out, either we can use it as a manure because it is almost degraded and it will be having high nutrient value, or if you want to further reduce the volume of the sludge, we can go for heat treatment like incineration, etc. And once it is the volume reduction is taken place, we can dispose it into land for land filling or something like that. So next class what we will do is we will be discussing in detail what are the stabilization process most commonly used, because that is very important. We have to design the stabilization process based upon the sludge nature and the sludge quantity. So we will see the sludge stabilization and other process in detail.